Hi guys, in this video let's look at the diazonium reaction handout here. The diazonium reaction is a common reaction of anilines where you have a primary amine on an aromatic ring, and of course this is called aniline, but it could be substituted like parabromoaniline. But the amine can also be on other aromatic systems such as the fluorine ring system. Now this chemistry is called diazonium chemistry because we make what is called a diazonium ion here as an intermediate. Di meaning two, aza is nitrogen. There's two nitrogens, and the nitrogen bonded to the ring becomes positively charged, but it's also triple bonded to another nitrogen. So where does this other nitrogen come from, and how do we get to this point? What is the mechanism for forming the diazonium? Well, first off, reagents. We use typically sodium nitrite, okay, nitrite, not nitrate, NO2, and an H plus source. And what this produces is HNO2. That's really what's being formed here. And this is called not nitric acid, that would be HNO3. HNO2 is called nitrous or nitrous acid. Now, nitrous acid is not a stable acid. You're never going to find it in a chemistry stockroom. But it is typically formed by taking the nitrite anion, which would have a Lewis structure that looks like that there, and then the sodium sits with that, and you have a salt, sodium nitrite. Sodium nitrite is stable, and it's commonly found in a chemistry lab. And if you treat it with a strong acid, well, we will protonate this oxygen and we'll make HNO2. Now, of course, the structure for HNO2 would be that there. There's your HNO2. We do this in situ, which means in the reaction. It's generated, nitrous acid is generated in the reaction. By the way, sometimes HNO2 is actually written HONO. Okay, that is, the O's are separated because if you look at your structure, it's HONO. And if you list it like that, you can say HONO. So two different ways to show HNO2 sort of formula. Here's your structure. But an aniline will react with nitrous acid to form a diazonium. Now there's going to be a minus. If we use HCl as the acid source here, then Cl minus could be the anion in your diazonium. If we use sulfuric acid as the H plus source, then this would be like a bisulfate anion to go along with your diazonium. Now when you do this diazonium chemistry, you make the diazonium, but it's not isolated, okay? Put brackets around this, not isolated. So it's going to be in solution. Typically it will remain dissolved. All right. Now, in solution is actually preferred in terms of safety. Solid diazoniums can actually explode. They're known to be unstable and can explode. So typically you do not want to isolate the diazonium salt. It's typically a solid because it is ionic salt. All right. Actually, some solutions could explode depending on the diazonium. Now, that's going to be a little bit more rare. I may mention more about this. But in the end, the diazonium is not isolated. They have been proven, this structure has been proven as what typically forms when you treat an aniline with nitrous acid. Then the diazonium, we can react it with various reagents and we can replace the two nitrogens there. And we can get a new group, a substitution reaction. Essentially, the two nitrogens serve as a leaving group, and we produce nitrogen gas. Okay, N triple bond N. And so you see, for this to form from here, these electrons just need to move on to this nitrogen, and you generate into gas. And since this is a gas, it will often form bubbles in your reaction as it escapes the reaction solution. Okay, before we look at these individual reactions, let's look at mechanism for forming the diazonium. We have, first off, assuming we've already protonated and generated into the nitrous acid in situ, I'll just start with that. And the first step is a lot like when we were doing a nitration, except there we were using nitric acid. We had one other oxygen here. But we also need more H+. And so the acid here can supply acid to generate your nitrous acid, but it also supplies acid for the next step, and that is protonation again of the oxygen. We get to here. Now, we've said before, anytime you can make a pi bond using a lone pair and kick off a leaving group, that's easy to do. Take these electrons and move them in here and kick that water off. And that's going to give an oxygen triple bonded to N, one lone pair on each, and the oxygen is positive, the nitrogen is neutral, plus water. And this is called a nitroso ion. If you remember when we did nitration, we formed the no lone pair on nitrogen. We formed the nitronium ion. Sometimes I think this is called a nitrosonium ion. I see in this handout it calls it a nitroso, and that's common also. Okay, but we're dealing with one less oxygen here. All right, but it's very identical to how you form both of these. Now in this case, if you have a aromatic amine there, it will actually attack this nitrogen here, even though there's a lone pair. You do have dipole. This oxygen's pulling, and these electrons can move back onto there. So the nitroso ion is electrophilic. I'm going to have my aerial this way. And so it attacked the nitrogen, double bond remaining here. Oxygen should now have 2 lone pairs. Nitrogen still has 1, and this is positive. And we see, ultimately, we're making a nitrogen-nitrogen triple bond. We start with a nitrogen-nitrogen single bond. All right. At this point, this oxygen is ultimately going to leave. How do you make oxygen a better leaving group? Protonate it, make it positive. Let's do a proton transfer. Now I could take it off here and make this completely neutral and then put it back on the oxygen, but we've also talked about how you can just do proton transfer, and that would give this structure here. At this point, we can consider resonance. These electrons move in here, and these electrons move on to oxygen. We're going to delocalize the positive charge. How do you stabilize a positive charge? Move electrons towards it. And this resonance structure is going to look like double bond here, single bond here, lone pair back on oxygen. It's now neutral, but now this N nitrogen is positive again. Now we have a double bond between nitrogen. We sort of just repeat the process, do another proton transfer. Protonate the N oxygen using essentially this as the acid. We get to there. Let's keep track of all lone pairs. And now, this is almost looks like the above steps. Up there, that was resonance. Here we do the similar. These electrons move in here, kick off the leaving group, and that gives triple bond in positive there. And there you go. There is your diazonium. So we lose water here. We lost water way up here. And now this is not resonance because we're actually breaking our molecule. So that's actually a reaction step. Where up here it was resonance because all we did was rearrange our pi electrons. And whatever anion we can say here, but it's all in solution. If it's all in solution, all the ions are dissociated. If it precipitated, it'd have to have a minus precipitate with the plus. But again, you don't want to precipitate. Now this is all kind of driven this way. Protonation, loss of water, and so the molecule breaking apart, and it's thermodynamically driven here. Now this water could theoretically add back, okay? The H2O added here and push these, and we'll actually do that next. After we look at diazoniums, we can actually do chemistry where nucleophile comes in here and adds to this nitrogen. And if water did that, we could envision going back to this. Okay, there's your mechanism for making your diazonium from nitrous acid. Now, we can replace the two nitrogens, as we mentioned. Let's start here. If you reacted a diazonium with either copper chloride or copper bromide, you replace the diazonium with the halogen there. Now, we're not going to look at mechanisms for these reactions. It's probably a radical reaction in most cases. And the copper helps promote the radicals. This is copper 1. All right? And by the way, the use of copper here was developed by the chemist known as Sandmeyer. And that's why a lot of diazonium reactions were called Sandmeyer reactions. Now with iodide, you do not have to use copper. That's because iodide is actually redox active and it will promote radicals. And so you can use just sodium or potassium iodide, much more common. You don't need the transition metal salt. Again, we're not looking at mechanisms here. These are just predict the product. So we have a new way to get a halogen on the ring, basically by replacing an amino group via the diazonium intermediate. Now, cyanide, you do need copper, and it's analogous to the copper chloride, copper bromide, and we can get a cyano group, okay, that's shown out structure, of course, where you would often maybe just show it like that. It's called benzonitrile. We can get a cyano group on the ring, and this is a very common way to do that from the aniline. Okay, let's look at a couple others which are a little bit more specialized. We can get a fluorine on the ring. Now actually this is very important because it's very difficult to directly put a fluorine on the ring because F2 is so reactive. But if you proceed via the diazonium, you first react the diazonium with tetrafluoroboric acid, it's called. And what this does first is it exchanges your anion with a BF4 anion. Now, this is boron with 4 fluorines, and the boron is negative. And it teams up with the positive diazonium, but this will actually precipitate. This combination of ions will come together and precipitate, which indicates that it's, for some reason, has a low solubility constant or nature. It must be a very strong ionic. But chemists have discovered this. Precipitates, you filter it off, and you get a dry diazonium. You got to be careful, though, because it could explode. But actually what you do is you then heat this, and it actually does explode. But you got to do it in a controlled manner. Plus nitrogen plus BF3. If you remember, we used BF3 as a Lewis acid before with alcohols. And you can actually, again, one of the F here serves as a nucleophile. Later on we will see, and we also saw in organic 1, we saw BH4 minus. And this was a hydride source, H minus source. This is an F minus source. All right. Some chemists or group of chemists developed this, discovered that this precipitates. Then someone said, well, what if we heat this thing? I'm sure they had a little, some explosions along the way, and they figured out how to do it safely. But they figured out that we could get fluorobenzene out of this reaction. So will explode. And by the way, let me add this. One of the scariest times I've ever had in lab is when I was trying to make a diazonium. then we were going to replace the diazonium, looking to make a compound with an SH group. That's not shown here. We'll look at OH. But we made the diazonium. I had a younger graduate student sort of working with me. I was a graduate student as well. And we were doing a large scale, fairly large scale. The flask was sort of the size of almost size of a volleyball. And we had made our diazonium. It wasn't of aniline. It was, can't remember if we had maybe a bromine at least or some other substituents. And after making the diazonium, we started dripping in the reactant to then ultimately get the sulfide. And we, from an addition funnel, started dripping. And all of a sudden it went bam! The flask didn't break, but it sounded like an old Volkswagen or a motorcycle or a lawnmower backfiring. Not quite as loud, but so I took off running, and I told the younger student to stop the stirring and stop the addition, and as I was around the corner, I heard it explode again. It kind of made another sound, and so we sort of stopped the reaction. We added a lot of water, diluted it out, and I can't remember if we decided to take another approach or we did it on a smaller scale. We should have been doing smaller scale to begin with, because you don't want to do potentially hazardous reactions on large scale. So you learn, you live and learn. A couple of years later, I read that diazonium sulfides are particularly explosive, and should have read that before doing the reaction, right? In the end, it was just a little scary because the sound it made. It was sort of some pressure coming out of the small flask, and it was a muffled sound. Okay, so got to be careful with these things. Couple other reactions here. If we take our diazonium and heat it with just water, all right, now it's going to be acidic water because, look, we're under acidic conditions. This is all the same flask. It's essentially water. We can replace the diazonium with an OH group. And now we have a phenol, all right? So we have a way to make phenols. Now this actually may be an ionic mechanism where the diazonium, okay, problem is, if you're going to show it here, why can't you show it with the other things, including with the halogens? But if we show this leaving, that would give that. But that's not a great carbocation because it's not resonance stabilized. You got to understand that. But if water then adds here, we could get this, and then something takes an H, maybe the chlorine or the chloride that's there. And you can see how we could get phenol, get something to write with here. And so that would be your phenol, okay? It could be this, but this is a fairly unstable carbocation. But if any of them are carbocation, that's the one that's most likely. Okay, See, the other ones you got to have copper, which really suggests it's more of a radical reaction, a single electron transfer. And these have been studied. It's mostly radical. All right. Regardless, let's really don't worry about exact mechanism. It's really a predictive product, a transformation reaction. The last one here is if you reacted with H3PO2, H3PO4 equals phosphoric acid. H3PO3 equals phosphorus acid. H3PO2 equals what? Hypophosphorus acid. All right. But it goes by a common name or an alternative name of phosphenic acid. It is a reducing acid. It will serve as a reducing agent because it likes to get oxidized. Okay, this is an oxidation. But if it gets oxidized, something has to be reduced. Okay, and it will reduce things. It will supply H's. Now, we're not going to look at mechanism, but it will supply an H, and we can replace the diazonium with an H. And so you just made benzene. So what you can do, and you can have students do this, you can have a student start with benzene and they could nitrate it with maybe KNO3 and H+, and then they can reduce that with maybe zinc and HCl. So they can make nitrobenzene, they can then reduce it to the aniline, they can then make a diazonium, and then they can reproduce benzene. And then you can have them do it again. This is where you have students do when they get in trouble and they need to stay after school. Okay, so why would you want to put an H there? Well, there are some cases where you would want to do that. Basically, it is a reaction where you can remove the amino group and go back to a non-substituent, just an H. All right. There are some specialized cases or instances where you might want to be able to do that. We may see one when we do some multi-step synthesis. Okay. That is diazonium reactions. These are the ones we need to know. There are a variety of other ones, like you can make thiols this way. There is a variety of other substitution reactions you can do with the diazonium. But just these for us. Here's an example diazonium over here. It looks like they're doing a classical replacement of the diazonium with iodide, but I give you a procedure. But you also have procedure that you're doing in the fluorine lab. Okay, another reaction of diazoniums is a so-called diazo coupling reaction. And here's a diazonium that I made from nitrous acid. Now, another reaction that they will undergo is if you throw in an activated aromatic, it will attack the diazonium, but instead of kicking off nitrogen and bonding here, this nucleophile will bond to this N nitrogen, as I alluded to. Now, this is an ortho-para director, and so I'm going to show a para reaction. We attack here and move these electrons here. Okay, and that will give, I'm just going to call this N-ring phenyl. Lone pair here, nitrogen, and now we have I'm going to say I used pi bond there, so I'm going to leave plus here. There would be pi bond here and here. Okay. This is where our phenol just attacked the terminal nitrogen, move the pi bond back here to become lone pair. Sigma complex, okay, it's turned upside down, but you should recognize that. There's an H here, right? And then something like whatever the anion here is can take the H and restore the aromaticity. And so this is our EAS. Instead of attacking, an acylium ion, we attack the diazonium. We do have to move these electrons this way as these come in. And we got this product here, a diazo coupling reaction it's called. It's kind of because it's two kind of larger molecules coupling together. But these type products tend to be dyes because they're very conjugated. This ring is conjugated through the double bond here with the other ring. We also have a lone pair that's conjugated. And as we saw with UV vis, highly conjugated systems tend to absorb in the visible region, and thus they tend to be colored. Since the lambda max is actually in the visible, there's a lot of visible absorbance, and thus they tend to be highly colored, not just maybe pale yellow, but deep yellow. But we can also get into like reds and greens and blues. Okay? Now typically, the aromatic that attacks your diazonium is going to be an activated aromatic. That's just most common here. And so phenol has an activating substituent. Here are some examples of azo dyes. You can take a look. This one's called Sunset Yellow. It's actually used to color certain foods like Doritos. So when you have a bag of Doritos, you think you're eating yellow cheese. It's really yellow food dye called Sunset Yellow. If you eat red maraschino cherries, they have plenty of F, D, and C red number 4. And if you look at this, this is the bond that was made because this is the activated aromatic, and that was the diazonium. All right? And so you need to be able to see, back this up to, okay, that's a sulfonic acid there. It's shown as anions. But that diazonium would react with this molecule here, and we see this is an ortho-pair director. It's an activator, and the reaction ends up going to this side. A little bit odd. This one looks more sterically accessible. Sometimes those types of things are hard to predict, but it looks like this ortho position here is what's reacting with the terminal nitrogen. Okay, this one here, it got hole punched. There's an acetal group there, but it's a yellow dye. It's called Solvent Yellow 124. It's used to dye diesel fuel in Europe so they can distinguish between diesel fuel and regular gasoline. But you see it here. It was an activated aromatic with this nitrogen group, and it looks like just regular diazonium here. Prontosil is actually an old drug that's the diazonium dye. And it was the first synthetic antibacterial, and it's actually made from this molecule here, and we first react it with nitrous acid to make the diazonium, then we come in and we react it with this dianiline. Okay, you got to consume your nitrous acid or you'll start making diazoniums here, but that's done. Now you just have diazonium, and when we put this in, these are ortho-para directors, and so we can do ortho to one and para to the other. These two sites being the same. The site in between is more sterically hindered, but that site ends up reacting with your diazonium there. Prontosil. Interestingly, in the body, this is actually metabolized back to this molecule, and it turns out that this molecule, known as sulfanilamide, is actually the active drug. Now, Prontosil was actually used back in the 1930s by, I believe, one of President Roosevelt's, or FDR's, grandchildren. You can read that story there. Yeah, okay, it begins with that. You can read that there. Okay. Multi-step synthesis. Multi-step synthesis. Please be working on that. Okay. I will do one here to close this out. Let's see if I back this up to that. Can I come forward and put on the ethyl group? Well, no, because this is an ortho-para director. Well, what if I back this up instead to ethylbenzene? Can I come forward? And again, the answer is no. It's an ortho-para director. I need a precursor that is a meta-director to get the meta relationship. All right. I'll let you think about that, and I think I'll create maybe a separate video looking at some of the multi-step synthesis there. Okay. By the way, the diazonium is in the benzylic chemistry. We looked at the benzylic carbon. The diazonium, we're looking at the atom bonded to the ring. Now, it's not a carbon, and it's not called a benzylic nitrogen usually. But it's somewhat analogous. We're looking next door to the ring. So that's why that reaction is including in this handout that's labeled as benzylic chemistry. Okay, guys. Also, in one of the next videos, we will be looking at other mechanisms, other ring mechanisms. Okay? So look forward to that. Okay, guys.